Welcome to Chapter 2, Part 2, The Modern Atom. So in this video, we want to talk about how we can tell different elements apart and what atoms really look like and what we can do with that. So atoms are really small, so we're going to use a unit called angstroms. And so angstroms are this A with a hat on it, and it's a unit of measurement. And so 1 angstrom equals 10 to the negative 10 meter. And so these are really small. And so the diameter of chlorine is 200 picometers or 2 angstroms. You don't need to memorize the size of any atoms, but you should know that angstroms are a unit conversion, and we're going to see that all the time. So part of the reason we want to use angstroms, and we're going to meet atomic mass units in just a second, it's really hard to think about something as, oh, those 2 atoms are 2 times 10 to the negative 10 meters apart. That's really not easy to think about. And so we want to be able to think about what that looks like. So we also know that atoms are really small. And so the heaviest atom on record is 4 times 10 to the negative 22nd grams for 1 atom. So instead, we're going to think about our atomic masses in terms of atomic mass units, or AMU. Now, atomic mass units are used when we talk about, in general, mostly only in Chapter 2. We will shortly move into grams per mole, but we haven't really gotten there yet. So 1 atomic mass unit is equal to 1.66054 times 10 to the negative 24th grams. So 1 atomic mass unit is really small. And so we can use that information as we think about different elements. So if we can weigh elements, and we can look at them, but how can we tell them apart? We know based on Dalton's second postulate that all atoms of an element are distinguishable from any other element. So it turns out that each element is distinguishable based on the number of electrons and protons found in a neutral atom. So it is important to think about what this means. So in this case, the protons are equal to the electrons. So in a neutral atom, both of those need to be the same. And so the protons and the electrons in any element are the same. So that means that when we think about carbon, it has 6 protons and 6 electrons. So a lot of times, or you may have seen something that looks like carbon 12. And so sometimes we'll see something that looks like this, a 12 over a 6 with the C in the middle. Let's draw that a little bit better. So in this case, the C is our element symbol. And that comes off of the periodic table. The 6 down here is the atomic number. And this actually comes, it is the number of protons or electrons. And so in this case, 6 means there's both 6 protons and 6 electrons. This 12 up here is actually something called the mass number. And it is, in fact, the neutrons plus protons. So what we see in this case is that the mass number basically gives you an idea about how heavy it's going to be, and the atomic number is the number of protons or the electrons. A lot of times we actually leave the atomic number off because the atomic number comes directly from the periodic table? So if it already comes from the periodic table and it's the same, we don't necessarily need it. Now, this mass number does change. So what does the mass number mean? Whoops. So atomic isotopes. So elements come in multiple isotopes. So each element can come in several different isotopes. For example, carbon has 4 isotopes. And so those isotopes are carbon 11, carbon 12, carbon 13, and carbon 14. So the difference between these 4 elements is in the mass number. So the important thing here is they have different numbers of neutrons. So they have different numbers of neutrons, which basically means that you can say that carbon 14 is heavier than carbon 11. And so the number of neutrons can be determined from the mass number. So if the mass number is equal to the neutrons plus the protons, we can get this directly from the atomic number. So we can see that these isotopes have different numbers of neutrons, but they all have the same protons because that's what makes them all carbon. And so we can determine the number of subatomic particles as long as we're provided the mass number. Okay, so for 197 AU, so we want to look for the protons, neutrons, and electrons. So the protons and the electrons are the same because this is a neutral element. We can get that information directly off of the periodic table. So the large number in the periodic table, so if we look at a square on a periodic table, a lot of times they look like this. So we'll draw for carbon. It says the number 6 up here in the top. And then down here at the bottom, it says 12.01. Some say the word carbon, and sometimes they're in different shapes. But this number up here, this is the atomic number. So when we look for AU, which is gold, we can find that in spot 79, which means that there are 79 protons and 79 electrons. So the neutrons are actually going to be 197 minus 79, which gives us 118. So to determine the protons, neutrons, and electrons, we need the periodic table, which in my class on any exam, you will be provided a copy of. So for strontium, 90, we have protons, neutrons, and electrons. So strontium is element 38, which means that there are 38 protons and 38 electrons. So the number of neutrons is 90 minus 38, which gives us 52. So why don't you take a second and pause to see if you can figure out the number of protons, neutrons, and electrons for vanadium. I hope you gave it a try. So when we look at the periodic table, we find vanadium as element 23, which tells us that there are 23 protons and 23 electrons. So if we want to find the number of neutrons, we're going to take 58 minus 23, and that gives us 35. So calculating the protons, neutrons, and electrons is relatively easy as long as you have the mass number. You could come up with the mass number if you're provided the number of neutrons and the number of electrons. You can do both in any case. So scientists decided that one of the things that was important is we want the ability to compare different elements to one another. So we want to create a scale. Instead of saying I have 5 grams of iron and 5 grams of carbon, we want to be able to basically be able to compare based on the number of atoms that are in there. So how can we do this? So scientists decided that carbon-12 would weigh exactly 12 grams. And so they did this because there are 12 protons, or there are 6 protons, 6 electrons, and 6 neutrons. So it weighs exactly 12 grams, like 12.00000 grams. And so then they created this as a scale. So all atomic masses are scaled to this weight. So all of the different masses are scaled. So one atomic mass unit is equal to 1.66054 times 10 to the negative 24th gram. If you calculate it to determine 1 gram equals 6.02214 times 10 to the 23rd atomic mass units. That number is really familiar. If you've taken a chemistry class before, it's Avogadro's number. And we're going to come back to that. So if you are like, I don't know Avogadro, that's okay. We'll get to that. So once we know this, we need to be able to account for the fact that there are isotopes. And so in order to do that, we're going to use something called a weighted average. So a weighted average means that the atomic weight is equal to the sum. So this sigma sign here means the sum of the isotope mass multiplied by the fractional isotope abundance and we're going to sum that over all isotopes. This basically means if we're trying to figure out the average atomic weight, so the number in the bottom of our carbon-6, 12.01, we need to figure out this value. And so we can calculate that based on how many isotopes there are and how much they account for. So if we look at chlorine, chlorine has 2 isotopes. So this here, this 17, is our atomic number. And so here are our 2 isotopes. This is our fractional abundance. And this number here is the mass. So if we want to calculate the average atomic, the mass for chlorine, we need to take into account for the fact that 75% of the atoms are carbon-35 and only 25% are carbon-37. So when we set up this calculation, we're going to use these numbers. So I am going to actually use I'm going to use 5 sig figs in this number just for ease of calculation. When you do this, you should use them all. So the atomic mass is equal to the mass of chlorine-35 plus chlorine-37. So for chlorine-35, it's going to be equal to the fractional abundance, which is 0.7578, multiplied by 34.969. And then we're going to add to this chlorine-37, which has a fractional abundance of 0.2422, multiplied by the weight, which is 36.966. So now we have this calculation. And so then we can plug this into our calculator and get a value. And so we would get 35.45. And so this should look something pretty close to what we see in the bottom of the square on the periodic table. So you might be wondering, what is fractional abundance? This is, so if we know that it's 35%, we want to make that into a fraction. So that would be 35 divided by 100. And this is also equal to 0.35. So we've taken our percent value and we just need to convert it into a fraction. So it needs to go into a fraction. Otherwise, this calculation up here would not work. And so the fractional abundance, you have to have the fractional abundance. And the fractional abundance is just the percent abundance converted into a fraction. So let's look at another example, because I think this calculation is important. So in this case, if the atomic weight of copper is 63.546 atomic mass units, and the dominant species is copper 63, which is 69.15% abundance and has a mass of 62.9296 atomic mass units. What is the abundance and the weight of the non-dominant species? So let's start with the abundance. How do we calculate that? Well, we know there's only 2 isotopes. Both of the isotopes have to add up to 100. So we're going to take our 100% and we're going to subtract 69.15%. And that's going to give us 30.85% abundant. So this is always true. The homework system will show you a different method in how to calculate this if you don't have either one of them. That is entirely possible algebraically, but it's not happening in. So in this case, what do we do now? Now we need to calculate, we're looking for the weight of the other species. So we know that we have the atomic weight. And we know that that's equal to the sum of the isotope mass multiplied by the fractional abundance. So of our 2 isotopes. So we can just set this up as an algebraic equation. So we have 63.546 atomic mass units is equal to copper 63 plus copper 65. So that equals 0.6915 multiplied by 62.9296 plus our isotopic abundance, which is 0.3085 multiplied by x. So then we can use algebra to solve for x. So in this case, the mass is equal to 64.9277 atomic mass units. And we need to check for our sig figs. So the smallest value we have is 4. And so in this case, we have 64.93 atomic mass units for the atomic mass, or for the weight of the other isotope. So the periodic table tells us a lot about different samples. So we've talked a little bit about how on the periodic table there are elements. That's not a square at all. So each element, if we look at potassium, it has the number 19 and 39.09683. So up here at the top, we have the atomic number. Then we have the atomic symbol. And down here at the bottom, we have the atomic weight. And so the periodic table, each of these elements, and so there are lots of different periodic tables, and I have provided one. I've provided several for you in our Canvas course, so you can go in there and look for that. You can also download one from the internet. Some of them will also come with the name. Some of them will come with other information. So before we look at a periodic table, I'm going to draw one up here. And this is roughly to scale. And so there are a couple of different regions that we want to talk about. So we call them in groups. So groups are the columns. And so we label them 1, 2, 3, 4, 5, 6, 7, 8 as we go across. These down here are not numbered. They are actually something else. So these are what we're going to call the transition metals. And so over here we have the alkali metals and the alkali earth metals. So over here in row 8, these are the noble gases. And so these are relatively inert. So these over here tend to be the halogens and the chalcogens. Most people don't tend to use the word chalcogens. They just say the oxygen-like family. We often see them involved in biological functions. So the rows down here at the bottom are called the lanthanide and actinide series. And we don't work with them all that often in Gen Chem 1. We mostly are going to work with the elements we find in the periodic table at the top. So this is a copy of the NIST periodic table. So NIST is the National Institute of Standards and Technology. And so if we were to zoom in on rhodium here, let me use a highlighter so we can see it and it won't color anything. So here we can see lots of information. So we can see that some of this information doesn't mean a lot to us. So if we were to look at this region up here and some of this information down here at the bottom, so far this is all information we haven't talked about. Some of it we will talk about later in the semester, but others tell you more about how this element behaves. And so as we look at different elements, the periodic table can show us different things. So we tend to read it left to right, and we can see that over here we have our groups 1, 2, 3, 4, so on and so forth. And so you can see that all of this information is available to you. So what do we need to know about the periodic table? So we, most of the time in Gen Chem, are going to use it by being able to determine, we're going to use it to calculate the mass, and we're going to use it to calculate the number of protons, neutrons, and electrons. So this is the mass that we will use, and this number here would allow us to determine protons, neutrons, and electrons, or protons and electrons, because that's the atomic number. The mass number needs to come from a different location.